All right, we are back talking about calculus, specifically derivatives, specifically today, differentiability. So differentiability refers to the ability for a function to have a derivative, for a function to be differentiated. So a function f is differentiable on the intersection of its domain and the domain of its derivative. So basically, a function is differentiable where it has slope. Okay, now that might seem weird to you at first. What does it mean if your function doesn't have slope? Well, remember, slope is undefined if there's a vertical place where there's a vertical slope on a function, which happens. Um, Also, a function will have no slope if the function itself is undefined. If the function is not continuous, that term from the previous chapter. Where does a function have a discontinuity? A function might have discontinuity like a vertical asymptote, or there might be a break in a graph or a hole in a graph. Those are discontinuities. So if a function is not continuous, it's not going to have a slope because the function is not defined there. There can't have a slope if there's not a point there. So like a vertical asymptote is probably going to be the most common place for that to happen. But there actually is some more nuance to where a function is differentiable, and we'll talk about that in just a second. But definition 2.1.5 is very important because throughout this class we're going to have to figure out, but like say before we can use a certain theorem, where is the function differentiable? Likewise, we'll have to figure out where it's continuous. So we've already talked about continuity in the previous chapter, but now we need to talk about differentiability. So we need to figure out where is a function differentiable. And it turns out it's differentiable on the intersection of a function's domain and the domain of its derivative. What does intersection mean? Intersection of two sets of numbers is the numbers they have in common, is the values they have in common. So the intersection of two sets is all the values they have in common. So example 2.16 is a very good example. It's the example we just worked a couple examples ago. Okay, we were finding the derivative of square root x. Now let's think about the function square root x. Okay, square root x has domain of positive numbers. So in interval notation, that's 0 to infinity with a bracket on the 0 indicates that 0 is a part of the domain. Okay. Now the derivative f prime. Now we didn't find f prime. We found we found a specific derivative. We didn't find the derivative function. So if you use the limit definition to find the derivative function of square root x, what you'll find is it's 1 over 2 square roots of x. So here f prime is 1 over 2 square roots of x, the derivative function. What's the domain of this derivative function? Well, notice it involves a radical. So at first you might say, well, it's all positive numbers, just like the original function. But since that radical is on the denominator cannot be allowed to be equal to 0. So we have to exclude 0 from the domain. So the domain of the derivative is 0 to infinity, not including 0. So what does this mean as far as where the function is differentiable? We would say that f of x equals square root x is differentiable on the intersection of those two sets. So what do they have in common? Well, their intersection is 0 to infinity. That is, the only number they don't have in common is the value 0. So we exclude x equals 0, and f of x is differentiable on 0 to infinity. So it's the intersection of those two sets. By the way, the intersection symbol, what we say here is that the intersection is 0 to infinity. It's like an upside down U. So the set 0 to infinity with a bracket intersect 0 to infinity with parentheses is 0 to infinity with parentheses. That is the intersection symbol. We say those two sets intersection. Their intersection is our solution here. Okay, so what it means if there's a point where a function is not differentiable, there's two graphical. Okay, if the function's defined, so here the function is defined at 0. You can plug in 0 into square root function, you get the square root of 0 is 0. So the function is defined at 0. What does it mean for the function to not be differentiable at 0 though? So there's two graphical manifestations. You can have, so assuming that the function is defined, so there's no discontinuity there. What's going to happen is if the function is not differentiable but the original function is defined, that means that you're either going to have a vertical tangent line or you're going to have a cusp, a sharp turn. Turns out you have a vertical tangent line here because the function turns vertical. Okay. So if you think about square root x, and this is going to be a terrible picture. It looks like that. It turns vertical for a brief moment there on the edge of that function. Okay, so that's why we have a point at 0 where the function does not have a slope, because it turns vertical for a brief moment. Okay. Now let's consider a couple more examples. Determine the intervals in which the following functions are differentiable. So to do this, we need to consider the domain of the original and compare that to the domain of the derivative, which means we need to find the derivative function. Okay, let's see. Here, let's consider a first. So what is the domain of 3x minus 2? So the domain of 3x minus 2 has domain, well, what do you tell me? It's a linear, so all real numbers. Has domain, all real numbers. So that's the domain of the original. What's the domain of the derivative? Well, I guess we need to find the derivative, so let's do that a little down here. Let's see. F prime, okay. We should all be in the same boat here because we've done this several examples now. Is the limit, as I'm going to use delta x's here. Delta x goes to 0. This is the original, the limit definition. So we're going to have f of x plus delta x. So 3 times x plus delta x minus 2. That's f of x plus delta x minus the original function, 3x minus 2, over delta x. Okay? So we need to simplify. No big deal. Equals limit as delta x goes to 0. Now on the top, really we just need to distribute a couple times. So we have 3 times x plus delta x is 3x plus 3 delta x minus 2 minus 3x plus 2 over our delta x. Okay. So what do we have here? Well, you have 3x and negative 3x, so positive 3x, negative 3x, positive 2 and negative 2. And what do you see? Usually we have to factor at this point. But notice everything on the numerator except for 3 delta x has added to 0. And now we have just a delta x on the bottom. And so I'm gonna, just to be clear here, sometimes students get a little too happy with just canceling everything off. Here, you would actually be on the safe side doing so, but that's what we're left with. And notice that we can divide out that common factor, which just leaves us with the limit as delta x goes to 0 of 3. Now, this might be a little confusing to you, and I could see where that might be the case. But we have a constant function. Okay, 3, it's constant. We're taking the limit as delta x goes to 0. And we have a property of limits that says, hey, if you're taking the limit of a constant function, then your limit is just always equal to that value, whatever that constant is. So here, Like in other words, think about it, there's nowhere to plug in a delta x. So whether you're plugging in delta x is 0 or a million, it makes no difference because we have a constant function, and so the limit is just 3. Okay? Now this might seem a little weird, but that's our derivative. But let's think about why this makes sense. F of x. F is a linear function. What's the slope? This is in slope-intercept form. Y equals mx plus b. What's the slope? 3. Of course our derivative is 3. And with a linear function, linear functions have the same slope everywhere. Doesn't matter where you look at on the function of a linear function, it's going to have the same slope. In this case, 3. So what's the domain of a constant function? Okay, so if you want to think about the derivative, f prime of x equals 3. It's a constant function. What's the domain of a constant function? Well, the domain, again, is all real numbers. Okay, so if the domain of the original function is all real numbers, the domain of the derivative is all real numbers, that means the function is differentiable for all real numbers because the intersection of all real numbers and all real numbers is all real numbers. If you have the intersection of two sets that are equal, you just have that same set all over again. So we can say, I guess in our conclusion, f is differentiable for all real numbers. So negative infinity to infinity. Okay? So f is continuous for all real numbers. So it has domain all real numbers. The derivative has the same, and so we have that the function is differentiable. It has slope everywhere. Now let's look at example B. All right, let's separate this off. This is going to take a little more work. Okay, so g of x equals 2 over x has domain what? All right, think about it for a sec. It's all real numbers except for 0. All real numbers except for 0. Okay, because I mean 2 over x, there's a vertical asymptote at 0. So the all real numbers except for 0 is the domain. Okay, now it's not guaranteed that the derivative has the same domain, so let's find the derivative and see what's going on. Since we used the regular limit definition for the previous example, let's use the alternative limit definition here. What is the alternative limit definition says? It says the limit. Sorry, it says f prime of c equals. Let's make that smaller. F prime of c equals the limit as x approaches c of f of x, the original function, so 2 over x, minus f of c, so 2 over c, over x minus c. Now, we can use the alternative limit definition just like this. I mean, usually we would let c be like a specific number, 5, 10, 6, something. But you can use it like this, no problem at all. Then c will just be variable here. Now, how do we solve this? Now, we have done examples just like this in chapter 2. The way I like to solve them is to notice if we multiply strategically, then we can get rid of the compound fractions. Compound fractions when you have a fraction within a fraction. Here we have 2 fractions in the numerator and then a nice denominator. But what if I multiplied up here? So by, let's see, xc. That is it's the least common multiple of these 2 denominators. But of course, I can't just multiply on the numerator and not do the same on the denominator. So if I multiply by x times c over x times c. Okay? What happens? Equals the limit as x approaches c. Okay, if I multiply x times c, what I get is okay, I'm going to distribute here, so I'm going to put parentheses like this. In fact, I'll do that as well. And on the denominator, by the way, I'm not going to distribute. I'm just going to write xc times x minus c. Okay. On the numerator, though, here I'll just write it out. So I don't want to skip any steps. I'm going to show you everything. So this is going to be 2 over x times xc minus 2 over c times xc equals the limit as x approaches c. I'm going to leave the denominator alone, xc times x minus c. Now on the numerator, watch what happens. X cancels out, x cancels out. So I have 2c left over. On the numerator, c cancels out with a c. So minus 2x. Okay? Now, at this point, you may be thinking to yourself, I don't really see where to go next because, well, I mean, I could factor a 2 out, and I mean, we'll see what happens. If I factor a 2 out, I'm kind of stuck at first. Limit as x approaches c. I'm going to have c minus x over xc x minus c. And you think to yourself, all right, I'm looking for a cancellation here. It's because it's that factor of x minus c on the bottom is what's causing problems. Because I can't plug a c in because I get c minus c is 0. But what if instead of factoring out a 2, what if I factored out a negative 2? You know, by factoring out a negative 2, that's going to reverse the signs of the terms. So this will be a negative c plus x. But negative c plus x, that's the same thing as x minus c. So I could, you know, I'll erase, make them match up perfectly. So we get 2 times, negative 2 times x minus c. And now those two terms cancel off, leaving us with the limit as x approaches c of negative 2 over xc. Now we're taking the limit as x goes to c, so we replace any x values with c. And so we drop the limit notation, we get negative 2 over c times c, which is c squared. There we are. So the limit, the derivative at c is negative 2 over c squared. F prime c. Now, don't let the c confuse you. C is just a specific value of x. I mean, if we had used the regular limit definition, our answer would have an x in it. But c is just a specific value of x. It's just a dummy variable. It doesn't really matter. So if you wanted to, you could say that we could say that f prime of x, this makes you more comfortable, is negative 2 over x squared. That is, the derivative function is negative 2 over x squared. So what we can do now is say that, hey, if I want the slope at any possible point, then just plug that x value into the f prime, and there's your slope. So if I want the slope at 1, plug a 1 in. So the slope at 1, well, f prime of 1, if you plug in a 1, it's negative 2. If you want the slope at negative 1, well, it's negative 2 as well, because when you plug in a negative 1 squared with a numerator of negative 2, you get negative 2. Okay? But that's not the point of this exercise. The point of this exercise is saying, well, what's the domain of this derivative function? Okay, so this has domain. Well, actually has domain all real numbers except for 0 again. So negative infinity to 0 union 0 to infinity. Okay, so where is it differentiable? So we could say f, oh, I used f's. Sorry about that. Let let me erase. That's G. I shouldn't change the. I shouldn't change the the function labels. It doesn't really matter, guys. I don't want to confuse you, but it doesn't really matter. F, G, H, whatever. It doesn't really matter. But I certainly should be consistent. So G prime, G prime. Okay. So let's see. We could say G is differentiable. It's differentiable on the intersection of its domain and the domain of its derivative. Well, in this case, both of those are the same sets. So negative infinity to 0, union 0 to infinity. Okay? So again, to drive that point home, the function will be differentiable on the intersection of its domain and the domain of the derivative. Now let's look at a situation where maybe those two things aren't the same. So in the previous example, they were the same. Like the domain of the derivative was the domain of the derivative. Sorry, the domain of the derivative was equal to the domain of the original function. Well, let's take an example. Hey, look here. So example 2.19 says demonstrate that each of the following functions is defined but not differentiable at x equals 0. All right, let's see what happens. All right, and we're familiar with absolute value, right? I mean, h here, h of x, if you remember from college algebra, has the graph. H of x, well, not equals. Let's just draw the graph. A graph of square root function looks like this. So there's h of x equals absolute value of x. So yeah, I mean it's continuous. The domain is all real numbers, right? So the domain, all real numbers. We learned that in college algebra. There's no holes, there's no asymptotes. So the domain is all real numbers, like so. Okay. Now, what about the derivative? Well, let's take a look at the derivative. So, let's use the alternative here. I think this would be a good place for the alternative. Again, you could use either one, I suppose, but the alternative limit definition I think would be probably good for both of these examples. So remember, we just used it. So we could say, let's see here. First go, there it is. We could say h prime of x is equal to, actually, let's say x prime of c, since that's how we phrased the alternative. H prime of c is the limit as x approaches c of f of x. So that's going to be square root of x minus f of c. So that would be absolute value of c over x minus c. Okay? Now, I guess I said specifically here, well, actually, this is the general case. I said let's consider 0, but we'll get there in just a sec. So here is the limit as x goes to c, h prime of c, which is the limit as h goes to c of absolute value of x minus absolute value of c over x minus c. But here, here's the thing. If c is positive, I guess there's a couple different cases here. If c is positive, then you can ignore the absolute value of c. And then if x is also positive, well, then you could ignore the absolute value of x, and then you can do some cancellations and such. But let's consider the specific situation at 0. Okay, so at 0, we would have, letting c be 0, h prime of 0 equals the limit as x goes to 0 of absolute value of x minus absolute value of 0 over x minus 0, which simplifies to absolute value of x over x, which we worked with functions just like this, limits just like this in chapter 2. What we remember the graph of the situation? The graph looked like this. You have +1 right there and -1 right there. Um, we had a discontinuity at 0, like so. That's what the graph looked like. So what does that tell you about this limit? Now, just because there's a discontinuity doesn't mean there's necessarily a problem, but here we see that there's a jump discontinuity. There's a break in the graph. So this limit does not exist. So since the limit does not exist, the derivative doesn't exist because a derivative is a limit. Okay? So since the derivative does not exist, we would say the function is not differentiable at 0. Okay? So since this is what the graph looks like when you have x equals 0, and actually it turns out that basically this is the graph that you get for any value of c except that it's shifted left or right. Okay? So it turns out that zero is the only problem here with this limit. Okay, for any other value, you'll either get for the limit you'll either get +1 or -1. Now, why does that make sense? Think about this picture over here. Here is the absolute value function. If you're on the right hand side of the absolute value v, the slope is 1. If you're on the left hand side, the slope is -1. So you would expect that for any other value except for 0, this function will simplify to either a +1 or a -1. Here, let's just try one out. Let's see. H prime of, let's say 1. So instead of 0, let's do 1. So h prime of 1, instead of plugging a 0 in, we're going to do absolute value of x minus absolute value of 1 over x minus 1. Okay, so this, I forgot my limit. Sorry about that. So let's see here. Limit is x approaches 1. Limit is x approaches 1 of absolute value of x minus absolute value of 1 over x minus 1. Okay, let's see here. Obviously, absolute value of 1 is 1. So you have absolute value of x minus 1 over x minus 1. Okay, obviously, if you try to plug in a 1, you get a 0 on the bottom. So we need to figure out how to do this. One thing that might be helpful would be to look at the two different cases, because we could write this as two separate limits, perhaps, or we could consider two separate limits. Because of absolute value of x is either positive or negative. So we could say, let's see, limit as x approaches 1. What if absolute value of x, if we're approaching 1, oh, you know what? I don't need this. Back up, back up. If we're approaching 1, what do we know about x? We're approaching 1. That means we're only considering x values very, very, very close to 1, which is positive. So if we're only considering x values which are very, very close to 1, we can assume x is positive. So if we're assuming x is positive, we could say x minus 1 over x minus 1, because the absolute value of x will be positive if x is positive. If we are only restricting ourselves to talking about a limit is x approaches 1. So notice cancel, cancel, which leaves us with the limit as x approaches 1 of 1, which of course is 1. So we get a fine limit, and that'll be the same thing will happen for every real number except for 0. So what's the takeaway here? The takeaway here is the limit does not exist, which means at 0, which means the function's not differentiable at 0. So if you want to talk about where it's differentiable, it's differentiable on negative infinity to 0, union 0 to infinity. Because that's the domain of the derivative, which, okay, so that's the domain of the derivative, intersect the domain of the original. So the domain of the original is all real numbers. The domain of the derivative is all real numbers except for 0. If you take the intersection of those two sets, you get where the function is differentiable, which is all real numbers except for 0. Okay, and what we have here, this is what we call a cusp, a sharp turn. Anytime you have a sharp turn on a function, that's going to result in a derivative being undefined. Sharp turn, anywhere you have like two slopes, either a sharp turn like that, or I mean even it doesn't have to be super sharp, but a situation basically where you have two parts of a graph intersecting where the slope from one side does not match the slope from the other side. That's when you're going to have what's called a cusp or a sharp turn. Okay, let's look at b. B is another function you should be familiar with, from college algebra. Here, let's sketch it over here. That is the cube root function. Cube root function looks something like this. Now that's not a perfect sketch, but that's close enough. Turns out that it turns vertical for just one brief moment. It has a vertical tangent line right here, just one brief moment. The slope is undefined at 0. Now let's show that that's happening. So clearly the function is defined for all real numbers. There is no asymptote, there's no holes, there's no gaps or anything. So the domain is all real numbers. But where is it differentiable? Where is it differentiable? It's going to be differentiable on the domain of the derivative intersect the domain of the original function. So the domain of the original is all real numbers. Let's see what the domain of the derivative is. Let's use the alternative again. H prime of c equals the limit as x approaches c of f of x, so x to the 1/3 plus 1 minus f of c. So that's going to be c to the 1/3 plus 1 all over x minus c. All right, let's see what happens here. Well, okay, so that's the general limit, alternative limit definition. Let's see what happens specifically at 0. So specifically at 0, replace all of the c's with zeros. So the limit as x goes to 0. So this is going to be x to the 1/3 plus 1 minus 0 to the 1/3 plus 1 over x minus 0. This is going to simplify a little bit to, let's see, we have 0 to the 1/3, that's 0, obviously. We have plus 1 minus 1, so we get x to the 1/3 over x. That simplifies just using properties of exponents. What? 1/3 x to the 1/3 over x. This is x to the first power. So this is going to be what? 1 over x to the 2/3 power. Now, what does that limit look like? Clearly, that limit is not defined. It doesn't exist. But let's see. We could maybe is equal perhaps to positive or negative infinity. If you consider from the right or the left we square and then take the cube root. So when you square those values, it's going to turn the value positive, the output positive, regardless if the input's negative or positive, because we're squaring. So I think this is going to be equal to infinity. There's an asymptote there, and it's going off towards positive infinity. In other words, again, remember that's a special version of D and E. So the limit does not exist. The alternative limit definition does not exist at 0, which means the limit does not exist at 0. The derivative does not exist at 0. So this function's not differentiable at 0. Now, it turns out we can do a similar kind of thing as we did in example A here. That is, there's not going to be a problem if we look at h prime of 1 or h prime of 10 or h prime of any number except for 0. 0 was the only problem because this function has a vertical tangent line at 0. So actually, in fact, let me do this. So let's say the domain of f is all real numbers. The domain of f prime, that is the domain of the derivative, is all real numbers except for 0. Just like it was with the just like it was with the absolute value function. Okay, so where is it differentiable? Actually, I should say f. F is therefore differentiable on the intersection of the domain of the derivative, all real numbers except for 0, and the domain of the original, all real numbers. So what's the intersection? Where do those two sets overlap? They overlap negative infinity to 0, union 0 to infinity. Okay? So just because a function is defined, this is the point of these two examples, just because a function is defined does not necessarily mean the slope is defined. And that relationship is theorem 2.11. So if f is differentiable at x equals c, then f is continuous at x equals c. But the converse is not necessarily true. Just because a function is continuous does not imply that it's differentiable. But if a function is differentiable, we know for sure it's continuous over the same values. So let's look at these few quick graphs here. Again, what theorem 2.11 says is if a function is differentiable, it's continuous. If a function is differentiable at x equals c, then it's continuous at x equals c. But the opposite, the converse, is not true. Just because it is continuous does not imply it's differentiable. So let's look at these. Example 2.110. Define or determine the intervals in which the functions are continuous and differentiable. Okay, so this is nice. Just looking at the picture, I mean, continuous means there's no holes or no gaps, no jumps. So where is this function continuous? Okay, continuous. Well, there's those two asymptotes. So everywhere except for those two asymptotes. That's going to be negative infinity to where negative 2. Union negative 2 to positive 2, union 2 to infinity. So it's continuous everywhere except for those two vertical asymptotes. All real numbers except for negative 2 and positive 2. Now, where is it differentiable? Now, when you're looking graphically to figure out where a function is differentiable, you're looking for three things actually. Is it continuous? So make sure the function is defined, and then make sure there's no cusp or no vertical tangent line. So here, this first example on the left, the only trouble are the two vertical asymptotes. There's no cusps, there's no sharp turns, there's no vertical tangent lines, so it's differentiable over the exact same domain. Is It's differentiable over the exact same domain, all real numbers, except -2 and +2. Okay? What about the middle one? Oh, let's see here. With the middle one, where is it continuous? All right, well, there's only one vertical asymptote, and that looks like the only problem with continuity. Um, so let's see, that's going to be negative infinity to 1, union 1 to infinity. So it's continuous except for that location of that vertical asymptote. Now, what about differentiable? Okay, of course, it's not going to be differentiable where there's a vertical asymptote. Okay, so that's a given. So negative infinity to 1 union 1. Okay, I should stop there though, because it's also not going to be differentiable if there's a cusp or a sharp turn or a vertical tangent line. And what do you see at 3 here? At 3, there's a cusp. It goes down, sharp turn, turns up. A cusp. So we have to say it's not differentiable at 3. So we have to exclude 3 as well. So we say all real numbers except for 1, because there's a vertical asymptote, and 3, because there's a cusp. Okay. Last example here. What do we have? Okay, we have a discontinuity, a jump discontinuity at 3. Okay, so there can't be slope at 3 because there's a discontinuity, just like there can't be a slope at 1 on the middle function or at +2 and -2 on the left-hand function, because the function has to be defined to even talk about slope. Okay, so we have, for sure, there's no slope at 3, so there's, and there, it's not continuous at 3. So let's, I guess, first talk about continuity. So it's continuous everywhere except for 3. So this is negative infinity to 3, union 3 to infinity. Okay, everywhere except for 3. But as far as differentiable is concerned, differentiability, or the intervals in which the function is differentiable, okay, what do you notice right here? It's kind of subtle, but that function, it's a cubic function. It turns vertical for just a brief moment, and there is a vertical tangent line right there. So if there's a vertical tangent line, the function's not differentiable at that value. So it looks like at -1 is where that happens. So -1, or negative infinity to -1, we have to exclude it. Union -1, okay, to what? All right, the next problem is at 3 because the function is not continuous at 3. So union 3 to infinity. So I guess the point, the overarching point of this exercise is that, a function, first of all, must be continuous to even talk about a derivative. So this left-hand example over here, where there's a vertical tangent line, it makes no sense to even talk about a derivative. So here, but the only trouble with these two functions were the vertical asymptotes. With the middle function, again, there's a vertical asymptote at 1, so that's a problem. We have to leave that out of the intervals of continuity as well as the intervals of differentiability. But in addition, there's a cusp at 3. So that's not a problem as far as continuity is concerned, but it's a problem as far as differentiability is concerned. There is no derivative at 3. The function is defined at 3, but not differentiable. And then there's a similar issue, a similar situation over here at the third example, where the function's not continuous at 3. So that makes no sense to even talk about a slope, because there is no slope at 3. There is no derivative at 3. But -1 is also an interesting situation because the function is continuous there. There is no gap, there's no hole, there's no asymptote, but there's a vertical tangent line, which means there's no slope at -1. So we have to leave out -1 from our intervals of differentiability. Okay? All right, so that wraps up differentiability versus continuity and figuring out graphically as well as figuring out via the limit definition where a function is differentiability. Is where is it differentiable. All right, catch you in the next video. If you have any questions, always feel free to reach out. Never hesitate to reach out. That's the key to success in this class. Ask questions when you need it. And of course, study every day. All right, talk to you soon.